Hi, everyone. Um, so I wasn't quite sure what to talk about today because I don't want to dive into a new topic yet, but I do want to be done with chapter 14. Um, the third problem in chapter 14 is kind of difficult, so I don't think we should bother with it. Um, and so rather than starting a new topic right now, I was just going to go over a few homework problems. One homework problem, which we talked about in office hours, but I'll present the full solution and leave you all with a question which I have, um, which maybe if you answer it, I'll give you some bonus points. Uh, so anyway, it's going to be kind of a grab bag of topics, but I think valuable. Just kind of reinforcing some of the important points before the exam next week. So I wanted to finish up this calculation of the area of a hyperbolic triangle. By now, many of you have solved this already on your own, but I'll present two different proofs. So hopefully, even if you've seen it, I'll show you a proof you have not seen, one of the two. So let's say we have a triangle in hyperbolic space that looks like that, with angles alpha, beta, and gamma. So this is an actual triangle. It's actually got vertices, nothing asymptotic going on here. The hint I gave you for how to solve the formula for the area in terms of the angles was use the following fact. So let's say we're in the hyperbolic plane, call it P. And which one? Well, let's say it has a radius rho. Okay. Then the area of an ideal triangle is, I guess we called it I rho, ideal. It's given by pi rho squared. We did that calculation. And another fact that we have is that the area of a 2/3 ideal triangle is, we have to say which 2/3 ideal triangle. So one with exterior angle theta is, I guess I called it A rho of theta, and it was equal just to theta times rho squared, which is equal to theta over pi times the area of an ideal triangle. So kind of like we saw with the loons, the area of a loon was some fraction of the surface area of the whole sphere. Here, the area of a 2/3 ideal triangle is some fraction of the area of an actual ideal triangle. And the picture here, a 2/3 ideal triangle has an actual vertex, and then the third side is asymptotic to the other two. So it's only got one actual vertex and two sort of asymptotic vertices. So that's why it's called 2/3 of an ideal triangle, because two of the three vertices are asymptotic. And then for this formula to be true, it's important that you realize that the theta we're talking about is not the interior angle at the vertex, but the exterior angle. So that's theta in this picture. And this is the 2/3 ideal triangle whose area we calculate. Okay, so to use these facts to find the area of this hyperbolic triangle, the hint I gave you was to extend each of the edges in a single direction. Okay. Now, of course, there's nothing stopping me from extending all the edges like this, but I don't need to. So I'm just going to look at 3 rays, the green, the blue, and the red. And the further hint I gave in office hours today was that you can build an ideal triangle out of this by look at, for instance, the red and the blue edges, and there's a third geodesic. We proved this in worksheet 1. There's a third geodesic which is asymptotic to both of them. And similarly, between the blue and the red, there's another geodesic which is asymptotic to each of them. And similarly, connecting the blue and the green, there's a geodesic which is asymptotic to the blue as I move left and the green as I move right. And let's give these sides names. And what I want you to notice is that S1 and S2 are asymptotic to each other. As I move down. Why? Well, they're both asymptotic to the red. They're getting closer and closer to the red geodesic, and arbitrarily close, in fact. And so therefore they must be getting closer and closer to each other. And similarly with S1 and S3 going left, and S2 and S3 going right. Okay, and so I'll have to move up here a little bit. The 3 black geodesics form an ideal triangle, which looks like that, right? And so what that tells me is that the area of this region in between the 3 black geodesics, I know it. It's the area of an ideal triangle, which is pi rho squared. And so the area of the triangle we care about, this one inside here, is going to be less than pi rho squared. And in fact, you can see exactly what it is. It's the area of the whole ideal triangle minus the part we don't care about, which is this part here. And so what we need to do is figure out a formula for the area of the yellow, right? Now, the key to doing that is to realize that the part that I just had yellow can actually be viewed as a bunch of 2/3 ideal triangles. So for instance, this region in here, what is it? Well, it's got, it's enclosed by this blue and this green geodesic, which meet at this black vertex. And then it's also enclosed by a third geodesic, S3, which is asymptotic to the blue and the green. That's exactly a 2/3 ideal triangle. It's got 3 geodesics. It's enclosed by 3 geodesics with 1 vertex and 2 sort of asymptotic vertices. And so this blue region is a 2/3 ideal triangle. And what's its exterior angle? Because that's what we care about for the area, right? It's the exterior angle. So the exterior angle is the angle at the vertex, and it's the part that's not on the inside of the triangle. And so in this case, the interior angle is this one, but we care about the exterior angle, and the exterior angle we can see is just gamma in this case. So 2/3 ideal triangle with exterior angle given by gamma. And similarly on the other sides. So this region here, it's also enclosed by 3 geodesics, where 2 of the pairs are asymptotic, and then the third pair, the blue and the red, actually meet at a vertex. This is also a 2/3 ideal triangle. And the exterior angle in this case is alpha. And then finally, the same on this side. This is a 2/3 ideal triangle. Oops. With exterior angle given by beta. Okay. And so finally, what we get is that the area of the pink one, the triangle we care about, is equal to the area of the ideal triangle, which looks like that, minus the area of the 2/3 ideal triangles, this, and then also the red one, and minus the area of the green one. Okay, and so what is this? Well, this is equal to the area of the black is pi rho squared. The area of the blue is, well, let me start with the red. The red one has exterior angle alpha. So minus alpha rho squared. And then minus the green is beta rho squared. And minus the blue is gamma rho squared. And so finally we get our formula, rho squared times pi minus alpha minus beta minus gamma. Now, sanity check, is this a positive number? It better be, because it's area. Yes, it is, because as we know from the last group presentation, the sum of the interior angles of a hyperbolic triangle are always less than pi. And so this thing in parentheses is positive. Okay. That's one way to solve it. It's probably the easiest way. Another way, it's kind of analogous to, you know, if you remember the proof on the sphere and you just tried to copy it, let's see what would happen. So the proof on the sphere used these lunes, right? And it looked at different lunes. So like, here's one of them. Here's one of them. And this was the third lune. So these are 3 lunes which cover the triangle with some overlap. And then we could take sort of the opposite lunes as well. So we could look at this one, this one, this one. Those 6 lunes together cover the entire sphere. With overlap. And you could use the fact that you know the surface area of the sphere, you know the surface area of the lunes, to kind of solve for the overlap. And the overlap was just the area of the triangle times the number of times that there was overlap. So that's how you could solve that problem on the sphere. If we try to do something similar on the hyperbolic space, we'll see what happens. So to do the analog of this picture, I would extend every geodesic as much as I could. So I extend all of these. Maybe I'll move this so I have a little more space. Okay. So what is kind of the analog of these lunes? Well, for instance, this red lune here, I take the red and the green intersection and I look at everything that kind of goes to the left of it. Okay. So I could do that here, but of course if I just look at everything here, it's going to be infinite, because the area of the hyperbolic plane itself is infinite. So instead of that, I'm going to choose a geodesic, which is asymptotic to the green and the red, and I'm going to use that as kind of the replacement for my loon. Okay? And this region here then, well, again, it's a 2/3 ideal triangle because it's got one vertex where the green and the red intersect, and then two asymptotic vertices where black and green approach each other and where black and red approach each other. And I could do the same at each vertex. So between blue and the red, let me extend this picture a little further. Okay, that should be okay. So between the blue and the red, I could draw a geodesic asymptotic to both blue and red, create this 2/3 ideal triangle. And notice that just like in the case of the sphere, now I have an overlap on the thing I care about, which is the actual triangle. And then finally, I could do the same thing with the blue and the green. And I get a third 2/3 ideal triangle whose vertexes where blue and green intersect. Okay, so I know the area of each of these, the red shaded region, the blue shaded region, and the green shaded region, so that's good. Is that enough to find the area of the triangle? Well, not really, because I don't know the area of this total thing, so I can't solve for the overlap. Well, what can I do? I see that there's these other 2/3 ideal triangles here. There's this one. There's this one. Extend that to make it more clear. If I draw a third geodesic asymptotic to the red and the green here, and then down here as well, I can draw another geodesic asymptotic to red and blue. Then I have another 2/3 ideal triangle there. So the way I've shaded these, I have 6 different 2/3 ideal triangles. 2 of them I shaded red, 2 of them I shaded blue, 2 of them I shaded green. And the thing I want you to notice is that the area of both of the red ones is the same. In other words, the area of this piece here, this 2/3 ideal triangle, is equal to the area of this 2/3 ideal triangle. They don't look like it in my picture, but they have to be equal. Why? Well, because the formula for the area of a 2/3 ideal triangle is given in terms of the exterior angle. So if this is the vertex, and I'm looking at this 2/3 ideal triangle here, the exterior angle is this, right? But that's also the exterior angle for this 2/3 ideal triangle. So in fact, these are congruent 2/3 ideal triangles. And if I rotate about this point by 180 degrees, I send one red shaded region to the other red shaded region. And so I know the area of these extra 2/3 ideal triangles I've added in. And it's a really similar picture to on the sphere here. I had to add 3 extra loons to cover the entire sphere. So if we can calculate the area of this entire thing, which I might call an ideal hexagon, because it's got 6 geodesics, but none of them intersect at vertices, but pairs of them are asymptotic, where they would have intersected. So if I can figure out the area of this ideal hexagon, then I can solve for the area of the ideal triangle. Solve for the area of the triangle inside, which is coming from the overlap of some of these loons. Okay, but what is the area of an ideal hexagon? We don't know. All we know is the area of an ideal triangle. How can we use that? Well, in this picture, there are some ideal triangles. So for instance, let me label these sides. Side 1, side 2, side 3, 4. So we know from worksheet 1 that between any two geodesics, I can find a third which is asymptotic to both of them. Let me choose a very visible color here. So for instance, between side 1 and side 2, there's a third geodesic which is asymptotic to both of them. Maybe that's not very visible. I'll try gray. Just make it dark. There's a third geodesic which is asymptotic to both S1 and S2. So this gray region in here, this is an ideal triangle. So I'm going to break my hexagon into ideal triangles. So for instance, what's another one? So between S3 and S4, I have another ideal triangle. And notice that this pink edge is also asymptotic to the gray edge. And then between this pink edge and S5, I can draw this orange, which is going to be asymptotic to both the gray and the pink. Kind of slides in between there. So this is an ideal triangle, this orange one as well. And then finally, S6 is asymptotic to gray. It's also asymptotic to orange. And orange and gray are asymptotic to each other as I move down. So this is also an ideal triangle. This yellow shaded region here. And so I have 4 ideal triangles, which together create this ideal hexagon, which I cared about. And so the area of the region enclosed by S1 through S6 is equal to 4 times the area of an ideal triangle, because it's made up of these 4 ideal triangles: brown, yellow, orange, and pink, which is equal to 4 pi rho squared. Now that's very interesting because it's kind of analogous to the sphere. Remember, the surface area of the sphere was equal to 4 pi rho squared, where rho is the radius of the sphere. And the surface area of the sphere was covered by these 6 lunes with a little bit of overlap. We have the exact same thing here, right? The area of the region, this ideal hexagon, is equal to 4 pi rho squared. It's kind of interesting that it's the same number. And, it was formed by these 6 things, which weren't lunes, but 6 2/3 ideal triangles. There were the 2 red ones, the 2 blue ones, the 2 green ones, just like in the sphere picture. And then you can solve for the overlap. In this case, those 6 lunes overlapped the actual triangle 3 times rather than the 6 times here, because here there was overlap on the back as well. In this picture, there's no back. And so you can use this calculation to also solve for the area over the overlap, and hopefully you get the same formula. Yeah, so I guess, all I wanted to say is if you tried to do your proof exactly the same as you started on the sphere, you could end up with a calculation that looked very similar, but you'd have to use this ideal hexagon to solve it that way. Okay, finally, this is just something random I was thinking about. So if you figure out a solution, please let me know. So my question is the following. Let me set it up. On the plane, this is kind of related to chapter 8, which some of the homework's on. Given a line and a point, so line L, point P, the shortest path from P to L is the line, well, the line from P which intersects L at a 90-degree angle, or pi over 2. Right, so if I draw a picture here, this is the shortest path. How do we know that? Well, we have the triangle inequality for one thing, right? But this is the shortest path, right? I guess you can see it by drawing circles, maybe. So my question for you is this still true? In hyperbolic space? I think the answer is yes. I'm pretty much 100% confident. But I haven't really thought of a proof yet. So let's say we're given a line L. And I'll draw a particularly nice situation where I can see what line's going to intersect at 90 degrees. Here's my point P. So you can see exactly which geodesic, because of the symmetry of this picture, which geodesic through P intersects L at 90 degrees. It's this vertical line, right? Is this line the shortest path? From P to L. I think this should be provable with the tools we have at hand. But I haven't come up with a proof yet. So, I could look at, there's lots of other paths connecting P to L, right? There's lots of other semicircles which intersect both. There's one. And I could reflect across this blue line to get this picture here, because of the symmetry, these are the same length, and so I get an isosceles triangle. And so another way to phrase the question, so equivalently, given an isosceles triangle, not even going to try to spell it correctly, in hyperbolic space, I can draw the perpendicular bisector, and I could ask, is the length, so this is 90 degrees, of the perpendicular bisector shorter than the length of the left or right side. And just to warn you that it's not totally obvious, let me show you that it's not true on the sphere. So on the sphere, let's start at the North Pole. I'll call that my point P. My blue line will just be the longitude line down the center. Now, if I use the equator as the geodesic that I'm intersecting, then any other longitude line, the distance is going to be the same. So in this case, the blue line's not shorter than the orange line, but at least they're the same length. It's not longer, right? So that's good. However, if I make my base of the triangle not the equator, but something a geodesic that I rotate down from the equator. So like something like this. So imagine taking the equator and just rotating the globe towards you, then the equator line is going to get closer and closer to kind of the outside circle. And now in this case, if I look at these longitude lines, the orange side, this is going to be shorter path to P than the blue. Okay, and so what I've drawn for you is an isosceles triangle here, where the perpendicular bisector is actually longer than the edges. Okay, I think that's unique to the sphere. I think it doesn't happen in hyperbolic space, but at least from the tools we have, I haven't come up with a proof yet. So if anyone comes up with one, I'd be interested in hearing about it. Thinking about this, I think, connects to some of the problems in Chapter 8, which are on the homework for next week, and it's not going to directly appear on the exam, but it's not a waste of time if you're studying for the exam. All right, enjoy the weekend, everyone.